Okay. So this is EE698G. If you still have any confusion on the course number, we are at lecture 5. So before I start with today's topics, I actually want to make a correction on something I said in the last class. So I mentioned that the flat region in this XOR PD is called as dead zone. The terminology dead zone is incorrect here. So the other statements I made remains correct. That is, it's a flat region. Therefore, the small signal gain will be 0. And the output is now not proportional to the, it's not linearly proportional to the magnitude of the input phase error. So all of those statements are correct, but the terminology dead zone is incorrect here. And also Ankit mentioned that it is similar to having a proportional controller. That is also, so it is probably incorrect to say that there is no feedback. And right now it is difficult to make such statements because we don't know how the complete system is configured, right? Once we know how the complete system is configured, we can make statements about what sort of controller it is, whether it's proportional controller, integral controller, or whether the feedback is open or, it is broken or not. These statements we can actually correctly make only after we build the entire system properly. And right now we are looking at a very simplistic model of the entire system. And without knowing the actual circuit components, we can't make any statements on it. In fact, you'll see that for most implementations, even if we have a flat region here, it's not proportional controller. It's mostly integral controller. Yeah. Correct. Yeah. That is what is actually happening. But to understand that statement, we actually have to see how it is completely built. Okay. So let's move on to today's lecture. So we are again looking at a few more phase detector architectures. Okay. So we were looking at the SR latch based PD. So let me quickly sketch out the latch. So we have this reset input and a set input. And this is my up and down. Just for clarity, this is what you would have earlier called as Q and Q bar. So now I can quickly write down the truth table. So this is 0, 0, 0, 1, 1, 0, 1, 1. So tell me what is happening when it is 0, 0. This is going to hold or retain the previous values. 0, 1, 0, 1, 1, 0, and 1, 1, 0, 0. Okay, so as usual, we take a case where I have, let's say, a positive 5 error. So I consider an in1, an in2, and then I'm going to now look at both up and down signals. So let's quickly sketch out these waveforms. So I have in1, I'm going to delay my in2 and sketch this into. All right, so now help me. What is the waveform for up and down? So in the initial case, so let me mark this as S, R, Q, and Q bar. So when S is 0 and R is 0, what is the output? It has to hold the previous state, but we don't know what the previous state is. So we'll not bother about what is happening beyond this point. So let's look at it after that. S is 1, R is 1. What happens to the up? So what? Yeah. So up is 1 and down is 0. Then both of them become 1. So this goes to 0. This remains at 0. Then I have 0 and 1. So down goes high. Up remains as it is. Then both of them become 0. That means it's going to hold the state. So much is okay. Now beyond this, if you look at it, it is a periodic waveform, right? So we have actually sketched the situation for one period. So I can simply repeat this waveform after this. So this is the output I will get. Okay. Now, what is the width of this pulse? It is same as the delay between these two, which let's now define as delta t. So this is equal to delta t. Can you comment on the width of this? What is it? T minus? So if I define this as my T naught, this is basically T naught by 2, right? So it looks like the information we need, which is delta T, is now embedded in the pulse width of the up signal. So if I take the average of up signal, I should get the correct result, right? But let's not make any conclusions yet. Let us repeat this for a case where phi 2 is negative. So can you sketch this case and tell me which signal has the information? So did you get a waveform like this? The up pulses are now T naught by 2 and the down pulses are now at delta T. So if phi error is less than 0, the information seems to be embedded in down. So what average should we take now? So in case 2, we have to take down average. But the whole point of the phase detector is to give us some magnitude which is proportional to the phase error, right? So it's not like we can somehow find out whether phase error is positive or negative and then go and choose a particular average. So what would you recommend? We have two signals. Would we be able to get the required output using some linear combination of the two? Huh? Okay. Okay. Average of what? So we have to do a linear, basically we have to do some linear combination of both up and down and then take the average, right? So let us calculate our VPD average as the average of up minus down. So can you tell me what this results? So let's do it for both cases. Let's say for case 1. So now VPD average is up minus down, where the delta T information is for up. So what expression do you get? So the average of up is delta T into VDD by T naught minus average of down is T naught by 2 into VDD by T naught. So this clearly becomes VDD by 2. Right? So let me take VDD by 2 outside. So what do I have? Delta T by T naught can be written as phi error by 2 pi, but I've taken a 2 outside. So this becomes phi error by pi minus 1. Okay. So now for case 2, what do you get? VPD average is still up minus down average. And the up average is now VDD by 2. What is the down average? It will be delta T into VDD by T naught. So this will again give a similar expression, VDD by 2 into 1 minus phi error by pi. So I have made a small mistake in writing this expression. Can you find out what the mistake is? Why 2 times? So I have taken common VDD by 2. So delta T by T naught will be equal to phi error by 2 pi. So this 2 gets cancelled because I have taken VDD by 2 as common. So in case 2, into was lagging in 1. So what is the polarity of phi error? Phi error has negative polarity, right? But in writing this expression, I didn't take that into account. So either I have to make this as plus, or to be more clear, I'll write it like this. Okay. So let's now sketch VPD average versus phi error. So we are finally going to configure our circuit to do something, right? So it's not like we can change, once the circuit is fabricated, it's not possible to take down minus up once in a while or up minus down once in a while, unless we parallelly implement both the choices and then choose the output as one of them, right? But it turns out if I choose VPD as up minus down and then do a hardware implementation of that, the value is still proportional to phi error. So what waveform do you get? It is 0 at it is 0 at pi, and then at 0 phase error, is it plus VDD by 2 or minus VDD by 2? Should be minus. So it will be at minus VDD by 2. And then you can check that up to 2 pi, this same equation will be valid. Similarly, here also, this will cross minus pi, and you'll get a similar plot. This is at minus 2 pi. So again, you can solve this for phase errors greater than pi, plot the timing diagram, and see that this equation is satisfied. So when phase error is equal to 2 pi, 2 minus 1, VDD by 2, right? Okay, so what is the monotonic range now? So I have a 2 pi range. I can choose to take from 0 to 2 pi or from minus 2 pi to 0. Doesn't matter. I have a 2 pi range. And is it linear? It is linear. So again, we have used very nonlinear blocks and then have obtained a very linear curve. Okay. Any questions on this? Okay, good. So now let's move on. Next, we are going to look at a very, very interesting phase detector called as phase frequency detector. This is in short called as a PFD. In fact, this is a very, very popular phase detector. And as the name indicates, this can actually give us some information on the frequency as well. And we will deal about this frequency detection part much later when we deal with loops that deal with varying frequencies. For now, our interest is in the phase detection part of this. So let me give you the circuit. So it consists of two D flip-flops. I connect both the D to logic 1. And the two inputs are given as clock signals. And I call the outputs as up and down. Okay. So now, as you can see, if in1 goes high once, right, the up remains high as 1 forever. Correct? Because the D input is always 1. Similarly, if into goes high once, the down input down will always remain as 1 because its D is also 1. So we need some mechanism to reset it. And for that, we connect a AND gate. So if up and down go high at the same time, then we reset both the flops. Okay. So this is the PFD. So now we have to do again, same old, same old. We have to draw the timing diagram for phase error greater than 0 and for phase error less than 0. This time you have to sketch in1, into. So here I am delaying the into. Now we have to plot up, down, and I'm also going to call another signal as the reset signal. And the reset signal is here. Okay, and we are going to call the delay of this AND gate as some value T reset. So with this information, can you plot these waveforms? So you have to plot in1, into, up, down, and reset. So help me out here. When does up signal go high? At the positive edge of in1, right? Similarly, down is going to go high with the positive edge in into. So the moment up and down goes high, your reset will go high, but after a delay of T reset. Right? So my reset signal has gone high here. So once the reset goes high, both the up and the down will come down. So once up and down have come down, which means now the reset has to come down. But there is again, because the reset signal is up and down. So if up or the down comes down, the reset also has to fall down, but it will fall down with a delay of T reset. Okay. So I will have a reset delay like this. So again, up will go high at the next rising edge. Down will go high at the next rising edge of into, and both of them will fall down like this. Is this clear? Okay. So tell me, what is the pulse width of down? This will be equal to T reset. What is the pulse width of up? If this is delta T, this will be equal to delta T plus T reset. Because this much portion is basically the same T reset that you see down here. Okay. So now if I take up minus down, I will technically have this delta T information in terms of the pulse width. So let's also quickly draw this for the second case, where phi error is a small value that is less than 0. I think this time you should be able to do this much faster. So again, you have to plot in1, into up, down, and reset. When does up signal go high? Goes high within 1. Down signal is going high much earlier. And once both go high, the reset signal will go high. So then they fall down. And after that, the reset also will fall down. Okay. So again, the width of the down signal is now delta t plus t reset. And the width of the up signal is just t reset. Okay. So we calculate our VPD average as up minus down average, because information is present in one of the signals depending on the polarity of the phase error. Okay. So can you calculate for case 1, what is the VPD average? Please calculate and tell me the result. So in terms of phase error, so what you'll get is some phase error into VDD by 2 pi. So what about case 2? So minus phase error into VDD by 2 pi. Everybody agrees? So phase error itself is negative. So if I'm writing the minus sign, I have to put a mod around the phi error. Okay. Is the calculation clear? Any questions on the calculation? Okay. I'm assuming this is clear. So let's sketch out the waveform. So I have phase error here. This is my VPD average. So here I have just said that the phase error is greater than 0. So up to what value is this analysis correct? So basically I'm asking you, this phase error is greater than 0 and it should be lesser than what? So you can slowly imagine your into waveform being pushed to this side. Is it pi by 2, pi, 2 pi? So as I'm moving my into this side, the width of the up pulse is also going to increase, right? At some point, that pattern will change. All the way up to 2 pi. Is that clear? So if I push this all the way up to 2 pi, you'll see that the width of the pulse will keep increasing. Correct? But the moment this into crosses 2 pi, for the first one, the pulse would be very large. We'll deal with that case. But for the second pulse onwards, it will be smaller pulse. So to clarify that, let us consider a case 3. Where you take the phi error to be slightly greater than 2 pi. So please sketch the waveforms. So my into is greater than 2 pi. So my up will go high here. The down will go high only here, right? So both the up and down will come down after a small delay of T reset. But next, my up is going to go high here. And the down will go high here. So up goes high here. Down will go high here. And then both of them will come down after T reset. So you have some initial transient. But if you remove this initial transient and consider only the steady state value, you see that the value has reduced again. So what is the pulse width? This is T reset. What is the pulse width here? So this is my delta T. So it's going to be T reset plus something. Can you tell me what that something is? This will be equal to delta T minus T naught. Okay. Which one down is it? Second pulse width. So anytime the falling edge, anytime you have a rising edge in into, you will have a rising edge in down. Is it clear now? Okay. So now if I calculate my VPD average, so I will leave this as homework to you. Please calculate the VPD average, but you will see that this number is smaller than whatever you would get for the value 2 pi. So if your delta T was slightly smaller than 2 pi, you would have had T reset plus delta T as the pulse width here. The moment it crosses one period, the expression changes. It becomes T reset plus delta T minus T naught. Therefore, your value is going to drop down. Is that clear? Okay, let's calculate this value. Please calculate what the average is and let me know. This will be equal to delta T minus T naught by T naught into VDD. So delta T by T naught is phi error by 2 pi minus T naught by T naught is 1 into VDD, right? So if I were to plot this, you will see that till the value of 2 pi, you will follow this expression, phi error into VDD by 2 pi. So you will get a curve like this. So the moment you cross this 2 pi value, you will have to solve using this expression. So if I put 2 pi here, what do I get? 0. So your curve is going to start again like this. Okay. And similarly, if I plot to the negative side, I will have this. And then it will have another waveform like this. So you can think of the continuous waveform like this. So this is 2 pi. What should this value be? 4 pi. This based on symmetry, you can say that this is 4 pi. This is minus 2 pi. And this is minus 4 pi. So etc. You can extend it infinite number of, for larger phase errors also. So here you can clearly see that when the phase error is positive, your VPD average is also positive, right? And when phase error is negative, your VPD average is negative, no matter how large a phase error you are taking. So this property is actually very useful in sensing the frequency of the signal as well. But like I said, we'll deal with it in much later circuits. Okay, so can you tell me what is the monotonic range now? What is the maximum monotonic range you can get? Minus 2 pi to 2 pi, which is a range of 4 pi, right? So earlier we saw circuits which gave us a monotonic range of pi, Then with SR latch-based PD, the monotonic range had increased to 2 pi. But the moment we have a PFD, the range is much larger. We have a 4 pi range. And this has a good locking point of 0, phase error as 0. Okay. So let's quickly note these also. The monotonic linear range that you can get is from minus 2 pi to 2 pi, which is a total range of 4 pi. Again, we are getting a linear characteristics, even though the circuit itself is nonlinear. Okay, now this PFD is also called as three-state PFD. So this is called as a three-state PFD. Any guesses on how this name came about? Where else have you heard this talk about states? Finite state machine, right? So that's it. This has come about from the concept of finite state machine or FSM, simply because in the regular operation of this PFD, there are 3 stable states. For example, let's start with a state where up is equal to 0 and down is equal to 0. Now, from this state, if I see a rising edge in 1, I go to the second state, which is up is equal to 1 and down is equal to 0. Now, if I see a rising edge in 2, I come back to the up equal to 0, down equal to 0 state. So there is an intermediate state here, which corresponds to up equal to 1, down equal to 1. But that is the temporary intermediate stage. You don't need any additional inputs to come out of that stage, right? It is not a stable state. Similarly, from here, if you get a rising edge in 2, we move to up equal to 0, down equal to 1. And with a rising edge in 1, you go back to 0, 0 state. So you basically have 1, 2, and 3 states. Therefore, this is called as a 3-state PFD. So this is the phase detector that we will be using in our DLL loop. So if you have any doubts, please ask. This is a very important circuit for us. Correct. Correct. You're asking how this whole DLL circuit will work in the presence of different voltages. So there are few adjustments that we need to do, but I guess that discussion will make sense after we have built the complete DLL. Okay. Right now, it might be a lot of hand waving because you have not seen the full circuit yet. But that is a very valid question. Okay, any other questions? We have only 1 minute left. I won't be able to start the next portion by then. So we can meet in the next class.